In the last lecture, we looked at eigenvalues and eigenvectors of matrices. And we had already seen in one place of a proof that relating eigenvalues and eigenvectors of matrices to polynomials can reveal something interesting. So we looked at the proof that said over complex numbers every operator has an eigenvalue. And to this end, we came up with a somewhat strange polynomial and looked at the roots of this polynomial, and this revealed that there needs to be an eigenvalue. Now, there is a much deeper connection between eigenvalues and polynomials, and one way to see this is looking at the characteristic polynomial of a matrix. And this is what we're going to do in this lecture. Before I go into the definition, let me maybe start with a motivation. So we are talking about eigenvalues and eigenvectors. So assume we have a matrix n times n. So A is an n times n matrix. And say V is not the zero vector. And assume we have that V is an eigenvector of eigenvalue lambda. So it satisfies A times V is lambda V. Now we have seen this already. We can rewrite this by bringing everything on the same side as A minus lambda, the identity, times V is 0. This is just by linearity. And this we can now describe as saying, so there's this vector V, which is not the zero vector, which is in the kernel of this linear map. So the kernel, so V is in the kernel of A minus lambda identity. And so if there's a non-trivial vector, not a zero vector, which is in the kernel of a linear mapping, we know that the rank of the corresponding matrix needs to be small, smaller than n. Rank of A minus lambda, the identity, must be strictly smaller than n. If you don't see why, think about there was the theorem that said that we can always find a basis of our original space in terms of the the pre-images of the range, of a basis of the range, plus the basis of the kernel. So if the kernel is non-trivial, has a dimension larger than 0, so at least 1, then the range of the linear mapping has to be at least, smaller, strictly smaller than n, and then the rank of the matrix, essentially, the rank of the matrix is the same as the dimension of the range of the image, the range of the linear mapping. So there we go. Now at the same time, we know that if the rank of a matrix is smaller than n, then the determinant of the corresponding matrix A minus lambda I has to be 0. Which means, and this is where we are heading it. Now observe here with this lambda, which we have in this expression. This is now a real number, it's the eigenvalue. And now comes the trick. What we now want to do is, we want to rewrite this expression where lambda is not the eigenvalue that we already know, but lambda is going to be a variable. And maybe for the sake of distinguishing it from a known eigenvalue, I'm going to write it as t. So I want to write an expression that looks like this one, but with a variable, and then hopefully this expression helps me to actually find these eigenvalues. So let me simply write down the definition. The characteristic polynomial of an n times n matrix A is defined as follows, so I write P A, so polynomial corresponding to matrix A, argument T, so T is the variable I've been talking about. I simply define it as the determinant of A minus T times the identity. So this is a definition. Maybe the first thing to figure out is that this thing that I've just written down, this looks like a very complicated object, the determinant of a matrix that has some variables as entries. So maybe let's simply look at an example to see what this really is, and that, in the first place, it's a polynomial. So let's simply look at an example. If we have A is A11, A12, A21, A22, just a 2 times 2 matrix. Then what is the determinant of A minus T times the identity? It's the determinant of, I write it once more, A11 minus A12, A21, A22, so this is A, minus T times the identity, so this is the identity matrix, 1, 0, 0, 1. Now I bring everything into one matrix. It's the determinant of A11 minus T, and on the other side of the diagonal I have A22 minus T. And all the other, so this is the general rule, it's like on the diagonal I always have to subtract T from the entry I currently have, and all the other entries are going to remain as they had been before. Make the parentheses a bit larger, like this. And now how do we compute the determinant of a 2 times 2 matrix? We know that it is A11 minus T, A22 minus T, minus A12 times A21. Okay? And now maybe just to make it complete, this is a polynomial and let's write it down. So here we have, it's a polynomial of degree 2, so the highest coefficient is going to be 2, like t squared, like the square here. And this we have we don't have a factor of -1 here. And then we have the linear factors plus t times, how often do we have t? We have it minus A11, sorry. No, my rubber is too large. Plus t times minus A11 minus A22. This is the term with like t to the power of 1. And then I have the last term A12 times A21 plus A11 times A22. So I did it maybe not in the most intuitive ordering, so this term is this term here, and the other one is that comes from the front for multiplying it out. Okay. So what we see here is, at least for this small example, the characteristic polynomial is really a polynomial, and the degree of this polynomial is 2, and this coincides with the size of my matrix. Okay. Now let's maybe make a couple of remarks or observations. So the first observation we have made, PA of t is a polynomial with degree n. So if we start with an n times n matrix, the polynomial has degree n. Okay. The second remark I want to make is about the basis. So observe now, how did we define this characteristic polynomial? Like the motivation was, we want to say something about eigenvalues and eigenvectors. And this is a property of the linear mapping itself. It's not so much a property of the matrix. Because the linear mapping stretches a certain vector by a certain factor. And this can be seen from the matrix by multiplying it, but ideally, okay. And now the characteristic polynomial, the way we defined it, it very crucially depends on the matrix itself. So the way we've written it here, and we see this also in the example, like the characteristic polynomial, maybe let me try to point it out. So here we have the expression of the characteristic polynomial in our example, and all of the matrix coefficients pop up in this expression everywhere. So it is hard to imagine that this expression does not depend on the basis. But this is a property that we would like, because if we now look at our linear operator on a different basis, we don't want to have a different characteristic polynomial. This would be somehow awkward and diminish the value of this object very much. Now, if you would have asked me, without giving me any backgrounds, you came up with this definition and would have asked me, do you think it's independent of the basis? I would have said no, because there are all these coefficients ai everywhere, and I would somehow find it strange, or would be surprised if it doesn't depend on the basis. But in fact, this is true here. So characteristic polynomial does not depend on the basis. And this is really cool, and the proof is simple. So you can, if you would get the assignment, prove that the characteristic polynomial does not depend on the basis. You could probably try it the hard way or the not so hard way. The hard way would be you change the basis of your matrix, you compute all the coefficients and then try to see it. This would end up in a mess, but you can write it down very concisely, easily. So what I now want to say is the characteristic polynomial does not depend on the basis. And what do I mean by this? Like, if you want to write it down formally, maybe proof. So consider a matrix A, and consider also a basis transformation matrix. Basis transformation matrix U. And then now what we want to look at is we want to look at the characteristic polynomial of the matrix U A U minus 1. So remember, if you do a basis transformation of a linear operator to matrix A, we need to multiply it with left and right with U and U minus 1, and then we have the operator in a different basis. And now the question is the characteristic polynomial of this guy the same as the characteristic polynomial of the original matrix A? And now let's simply do the math, and this is surprisingly simple. So we look at the deterministic so the characteristic polynomial of this matrix is now U A U minus 1 minus T times the identity. That's the definition of the characteristic polynomial of this new matrix. Now what we do first is we keep the beginning of this expression, but we replace the identity matrix by U times U minus 1. Let me write it down. U times U minus 1. So far nothing has really happened because the identity matrix is the same as U times U minus 1 for every invertible matrix. And now by all the rules of how, like associativity and so on, distributive properties, we can now rewrite this expression in a more convenient way. So what I want to achieve now is I want to have the U at the beginning and the U minus 1 at the end, and in the middle I want to have the operator that I'm really interested in. Maybe I write it in blue. And this is A minus T times the identity. And I can do that. So if you look at the expression, oh sorry, here I see I made a typo. So this needs to be, and I need to make it in black. This needs to be U minus 1 here. Hopefully you have made, and maybe here I also do it, this is also not written in a very clear way, just to make sure, like this. Okay, so now we're on the last line. And now only one remaining step is to be done. We know that the determinant is multiplicative, so we can like if we have a decomposition of the operator as a product, we can write it as a product of the determinants. So this is determinant of U times the determinant of the blue object A minus T times the identity times the determinant of U minus 1. And now finally, I hope you see, everybody sees this now, the determinant of U and the determinant of U minus 1, they cancel. Together they give 1 because they are the inverse of each other. So all that's left is the determinant of A minus T, the identity. And now if we look at from the beginning and the end, what we see is the determinant of this original matrix, of the transformed matrix, like the characteristic polynomial of the transformed matrix is the same as the one of the original matrix. And this is what we wanted to prove. Okay, so this is neat and simple. Now, the next, so what we have seen now, the characteristic polynomial does not depend on the basis. What we now want to say is the characteristic polynomial gives us the eigenvectors and the eigenvalues in particular of the matrix. So the roots of the characteristic polynomial correspond exactly to the eigenvalues of matrix A. So this is one of the statements. Formally, if you want to prove it, you need to invest a bit of work, but I think based on the intuition, the fact is reasonably clear. Now it depends on which is our field that we're currently looking at, and I said already, so eigenvalues here, it's really important whether we look at the complex number or the real numbers, and this is exactly the point where we can see that. If we are on the complex numbers and we have a polynomial of degree n, it always has n roots and can be written of a product of n linear terms. So over C, the characteristic polynomial always has n roots. This is the fundamental theorem of algebra. So the matrix has, I just write n eigenvalues, and they are not necessarily distinct. So it might be that one of the roots occurs with a factor of, with an exponent of 5. The important thing here is to note that this is of course not the case over R. Over R, we could have a polynomial that doesn't have a single root, or we can have a polynomial of degree 20 and it has 5 roots. So you can construct whatever you want here. So what else do we have? Over C, well, this is maybe not such an important property. Over C, the matrix is invertible if 0 is not an eigenvalue. And in fact, I think this must also be true over R. I'm sorry. So no matter whether you're in R or in C, the matrix A is invertible if and only if 0 is not an eigenvalue. And because I was just confused myself, let me simply give you the reason. If 0 is an eigenvalue, then we have A, so then there exists an then there exists a vector V with the property A times V is 0 times V, so A times V is 0. So the kernel of this linear map is not empty, so the thing is not invertible. So if you want, kernel of A is non-trivial, A not invertible. And this argument also works the other way around. If A is not invertible, then the kernel is non-trivial, then you can pick exactly one such vector that is in the kernel, and for this vector you have that it is an eigenvalue of eigenvalues, an eigenvector of eigenvalue 0. Okay, so this holds always. What else do we have? This one I have already mentioned. Let me just check my notes. Okay. Some other properties which are maybe not so surprising, but let A be a linear operator on the vector space V and lambda an eigenvalue of A. Then lambda to the power of k is an eigenvalue of the operator A to the power of k. And intuitively from the geometric meaning of an eigenvector, this is also clear. Like if lambda is an eigenvalue with a certain eigenvector v, it means the vector v is being stretched by a factor of, say, 5, if my eigenvalue is 5. If I apply the mapping once more, I get another factor 5 and another factor 5 and so on. So if I apply my mapping several times, each time this vector is going to be stretched by a factor of k. of lambda, sorry. So all in all, it's going to be stretched by a factor of lambda to the power of k if I repeat that thing k times. The other thing maybe it has a similar geometric meaning, but is important as well. Let A be invertible, and lambda an eigenvalue of A. Then we already know something about eigenvalues of A minus 1, the inverse. Namely, 1 over lambda needs to be an eigenvalue. 1 over lambda is an eigenvalue of the inverse of the matrix A. And again, from a geometric point of view, this makes perfect sense. So assume I have a linear mapping and it stretches a vector v by say, the factor 2. So the original vector v has, say, length 1. After I apply the mapping, it has length 2. Now I want to invert the mapping. Inverting the mapping means I need to take this vector of length 2 and bring it back to the original vector of length 1. So I need to multiply it by 1 over lambda, the inverse of the stretching factor I had in the first place. Okay, so from the geometric meaning, this is also clear. I mean, all these statements, I just mentioned them this way. Formally, you have to prove all of them, of course, and sometimes also writing down the formal proof is not so easy, depending on which definition of eigenvectors and eigenvalues you start with, and characteristic polynomial and all these kinds of things. But anyways, here we have it. Okay, that's all the observations I wanted to make. And now I want to introduce a final notion, namely what is the multiplicity of an eigenvalue. And unfortunately, there are two different notions of multiplicity which not always coincide. Let me write it down. For an operator A, operator or matrix, and you can choose which word you like more. For an operator A with eigenvalue lambda, we define, first of all, its geometric multiplicity. The geometric multiplicity of the eigenvalue lambda is the dimension of the corresponding eigenspace. Geometric multiplicity is the dimension of the corresponding eigenspace. We denoted it as E lambda A. So the dimension of the eigenspace is the geometric multiplicity. And now we also have a notion of the algebraic multiplicity. The algebraic multiplicity of an eigenvector, of an eigenvalue. Maybe underline it. The algebraic multiplicity is the multiplicity of the root lambda in this characteristic polynomial. Is the multiplicity of the root lambda in the characteristic polynomial. Now these are two different definitions. Once I look at the geometric multiplicity, which is the dimension of the eigenspace. For the other thing, I look at the exponent, like the multiplicity of the root in the characteristic polynomial. And in general, the two do not coincide. In general, these two notions do not coincide. There are cases where they coincide, and we're going to see that later, but in general they do not. Maybe let me make one more remark about how can you actually compute eigenvalues and eigenvectors. Just as a final computing, maybe I just write eigs So as I said, Eig is always my abbreviation for either eigenvector or eigenvalue. And here we go, so we want to compute maybe both of them. So what you can do is you can say, you write down the characteristic polynomial and then find the zeros, the roots, find the roots. Then you already know the eigenvalues. And then to compute the eigenvectors, you now solve you have a linear system to compute the eigenvectors, solve the linear system, which is then A times x is lambda x. So the x is the unknown, lambda and a are known because you already know the eigenvalues, and then you can compute. You can solve that and compute it. And depending on your linear system, you might have you should have one solution. Otherwise, you did something wrong with your roots in the polynomial. So there should be at least one solution. And in fact, the multiple of the solution is always also a solution. And then if your eigenspace has a higher dimension, you might find more solutions. This is the standard kind of theory of what are the solutions of a linear system. Now, in practice, this is not how you're going to do it. And actually also in theory, like if you have a 2 by 2 matrix, you can of course do that. If you have an n times n matrix and n is larger than 2, then finding the roots of this polynomial is difficult. You don't know how to do that. So this is not a method that is really practical. And in practice, people use different numerical methods for doing that, and we're going to discuss that later. For now, it's just if you ever have to solve an exercise or an assignment saying compute the eigenvectors, this might be a strategy for doing it.